projectile motion. Now, the definition of projectile motion is very simple. I'm not going to get into the complicated ideas behind it. It's really not that bad. Projectile motion is just simply 2D motion, two-dimensional motion, where in the y-axis you have free fall, and in the x-axis you have constant velocity. In the y-axis you have free fall, in the x-axis you have constant velocity. Two-dimensional motion. There is something moving in both the x and the y. It is free of all forces except gravity. Say that again. It is free of all forces except gravity. So, I mean, the only force is the force of gravity, Fg. Okay, that's it. All other forces can be neglected. Now, since it's technically going at constant velocity in the x-axis, we end up getting a pretty cool idea out of this. In that something that is dropped and something that is thrown horizontally will hit the ground at the same time. Something that is dropped and something that is thrown horizontally will hit the ground at the same time. The purpose behind this is to point out that you can treat the x and y axis as two completely separate objects moving at two completely separate times, and then recombine them at the end. In other words, you can pretend something that's moving two-dimensional, projectile motion, is two separate objects. One object moving in the x-axis, another object moving in the y-axis. The times will be the same. Their motion will be the same. So, a little demo here. Who showed the red one? Okay, here we go. Yeah, so it's still 9.8. Thank you very much. It's still 9.8 for the acceleration of gravity. In other words, if I were to try to graph this out with what's happening, thank you, Mr. Tesla. Golf ball. If I were to graph this out, if I have a cliff, okay, and something is shot off horizontally, like this, with some initial velocity, u equals, I don't know, say 15 meters per second. What motion is that ball going to experience? A curve downwards, an exponential curve downwards, right? It's going to go something like that, right? That's projectile motion. The curve is going to get steeper and steeper and steeper, right? Because gravity is pulling and it's accelerating, getting faster and faster and faster in the y, while going at a constant velocity in the x. The cool part about this, in the y-axis, if you just drop something, after 1 second, it hasn't traveled very far. After 2 seconds, remember, it's accelerating, right? So it's gotten faster, it's traveled farther, right? So after 2 seconds, it's traveled a little bit further. After 3 seconds, it's traveled even further than that. For every second, it travels a farther distance, right? That's acceleration. In the y or in the x-axis, it's going to move at constant velocity. That means at every point, it comes out. This is the initial part. So let me jump over to where it's actually curving. Okay. At every point, 1 second. So it's actually kind of being launched from over here. Okay. 1 second. 2 seconds. 3 seconds. Now check this out. And I know these lines aren't perfectly straight. I apologize for that. Okay. In fact, that one's way off, right? What should have happened? And let me reline this guy out. This is bad. 1, 2, 3. your motion in the x-axis, the distance stays the same each time. That's what I'm doing with my poor drawing skills. Okay?
What is that?
Even though in the x-axis the distance stays the same, constant velocity. Okay? In the y-axis you're accelerating. Notice how each second it clicks off farther and farther and farther. Okay? So that's the idea. You can divide motion, projectile motion, into x and y components. Solve the x and the y separately, and then add them back together. That's why adding vectors and dividing into components is so important. It's going to come back every single unit. You name a mechanics unit here at the beginning of the year, you will see this. You're going to see components all the way until January, and then after that too, here and there. Okay? It's going to be here the entire year, vectors, components. Get comfortable with it. Right? So rules for how to do free body diagrams. Okay, or excuse me, how to do projectile motion. Getting ahead of this. 1. As always, draw and label a picture. 2. Break everything into components if it's not already in components. Break everything into components. 3. Write down everything that you know and each individual axis and what you're looking for in each individual axis. In other words, whenever you divide things into components, you have broken this one problem into 2 separate problems. You've got a physics problem that goes with the x-axis. You've got a physics problem that goes with the y-axis. They are 2 individual problems that you will solve. Okay? Solve for what you're looking for and the axis it contains. Now, step 4 only happens whenever life is oh so lovingly easy. Okay? In other words, you have everything that you need in one of the axes to solve for what you're looking for, and you just solve. Odds are, though, you aren't going to have that. Odds are you won't be able to do step 4. You'll have to jump to step 5. If you do not have enough information, there isn't enough information given to actually solve for what you're looking for, jump to the other axis. Solve for something that is also in the axis that you were originally in. Most of the time it's going to be time. Plug that in, step 6, now you can solve. Let me re-emphasize that time idea. The number one thing that you're going to carry over is time. Time is exactly the same, as we just proved, right? Whether something was launched as a projectile horizontally or dropped, they hit the ground at the same time. Time is the same in the x and y axis, even though one's experiencing the acceleration of gravity and another is going at constant velocity in the x-axis. Time is the same for both of them. If you take physics in college, every last one of you should, no matter what you're doing. I don't know if I've given you this spiel, but here it is. If you're going to be doing anything in math and science, you will be taking physics. Period. If you want to go into any sort of medical field, you will be taking physics. If you want to go into business, if you want to go into finance, if you want to go into whatever other thing that is way the opposite direction from math and science, you will still be required to take a science. Now, in college, they'll give you a choice. Your science can be botany. Your science can be geology. Your science can be, if you want to rock some chemistry, chemistry, right? Your science can be physics. You're interested in what?
They got a nature study one in the college. I was like, man, it's a nature walk.
I don't even want to know what college that is, that it counts as a science. Don't tell me. It can be whatever. It can be, you can take any science. Now, here's why I say you should take physics. if you take geology, it all depends upon the professor lots of times. The professor could be one of two people. You're going to take this basic level geology, and everyone else has the same idea as you. I'm going to take an easy science. I'm going to take geology, right? I'm going to study rocks and everything. And the professor, for a little bit, seems all nice, you know, but in reality, he's kind of angry because he's got a room full of 200 people that aren't majoring in what he wants them to major in. He's got to teach all these people who don't give a darn about his subject, right? Not a few of them, a whole dang bunch of them. That makes him mad. And so what he starts assigning is memorize every last flippant type of rock that has ever existed in the Earth's crust. You know, and then you have to memorize all these different types and shapes, and it gets dadgum ridiculous. People fail sometimes in those courses.
Adam?
Yes?
Birch?
Yeah, I'm sorry.
Thank you.
Attendance. Physics, on the other hand, now, I can say this. Sometimes you get a professor who's actually reasonable in those courses, right? They understand that you have a life, that you actually have a major, and that you're there to learn. And they're not bitter about you not learning their subject, mainly. So they do take it to the level that it should be at. Right? Not that bad, but still interesting. On the other hand, if you take physics, now that there are, let's say at UGA, there are 3 levels of physics. There is the 12,000 level, okay, which is for physics majors, engineering majors, pre-med. We're talking hardcore science levels, okay. There's the 1100. That would be mainly for, depending on what you want to do. That's math. That's related fields that kind of are related in science, okay. And then there is the 1,000 level. Okay, the 12,000 is calculus-based. The 1200. The 1100 is trig-based. That's what you're doing basically right now. Okay, we're not going to get as far and as deep as they will in college, but we're doing that right now. You'll see all the exact same things come up again. Then there's the 1,000 level. Now, the 1,000 level is meant for the business majors, right? And questions in the 1,000 level is things like, which way does gravity go? And you answer, well, right? And you're all so happy, right? The 1,000 level has a little bit of math, but it's a lot of just conceptual stuff, all right? And having had physics here, the 1,000 level is going to be easy, at least as long as you don't get some psycho professor. Sometimes that does happen, all right, in college. You're going to get it, okay? But the 1,000 level will be easy. Why take the risk with the geology with 200 other people in some of the course that you've never taken before when you already have physics knowledge, right? You already have the knowledge to pass the class. All you got to do is show up, take notes, make sure he doesn't teach something new that I didn't get a chance to go over, and then go make hundreds on your test and walk out with your A. Plus, I mean, which are you more interested in? Talking about rocks all day and holding up a rock, staring at it? Or physics, where you're actually going to get to the lab and launch things across the room. For example, the demo that they do at UGA, they have more resources, obviously, than I. The big hall where they teach physics in, they put a baseball on one side of the room at the ceiling, and they're going to launch it horizontally. They put a glove. I think they actually use a basket. They put a little basket on the other side at the ceiling, same height. They launch the ball and drop the basket at the exact same time. Exactly what Daniel and I just did, right? Okay? Except since the basket's falling over here, and the baseball's coming this way, where does the baseball land? In the basket. Okay? What would you prefer to take? That kind of cool course? Or something that you stare at rocks all day? Right? I mean, take the easy physics. Take the easy physics. Rocks for jocks doesn't actually exist hardly anymore. Now, go through this idea. Go through this idea. Use your steps. That is, use your steps. Draw, label a picture, break everything into components, write down everything you know in each individual axis, solve. If you can't solve, go get more than likely time from the other axis, plug in, solve. So, example problems. Horizontal launch is what we're dealing with first. We already did a little horizontal launch demo, so I'm not going to worry about that right now. I'm just going to jump straight into it. horizontal launch, your initial velocity in the y is 0. Your initial velocity in the y is 0. I mean, think about it. If you're launching horizontally, here's our cliff. If I'm launching like that is my initial velocity, what axis is that in? The x. And since there is no angle, it's at 0 degrees, what's the y component? Here's that, right? And the x component is whatever that initial velocity was given to me. Okay? Cosine of 0 is 1. 1 times that initial velocity is the initial velocity. So horizontal launch. Uy, 0. Ux, the given initial velocity. Okay? The given initial velocity. Okay. So, a couple problems. One, a rock is thrown horizontally off a 200-meter cliff at 23 meters per second. How far away from the cliff, the base of the cliff doesn't land? So I've got a cliff here, right? I'm going to throw a rock like that, 23 meters per second. That's what U equals. S here, or maybe I should drop my S for a second and I should use Y, okay? Doesn't matter. Y, the displacement in the y-axis, 220 meters. Displacement in the y-axis, 220 meters. Now, this ball is going to follow some trajectory like that, right, and land. And my question is, what is x? What does x come out to be? All right, so now I'm going to set up my two axes, x and y, and I'm going to write down everything I know and what I'm looking for. Now, on the x-axis is constant velocity. What are the three variables? There's only three variables you have to deal with for constant velocity. What are they? And velocity. Right, v equals s over t. Right, all you have to deal with is velocity, displacement, which I'm going to use x, and time. That's it. All you have to deal with. Now we know the velocity in the x-axis. What is it? 23. Since it's constant, the initial is the same as the final, is the same as the average. It does not change. The velocity is always 23 in the x-axis. The x displacement is what I'm looking for. How far out does it go in the x-axis, right? How far out does it go on the x-axis? And I don't know the time either, right? That wasn't given to me. Let's go to the y-axis. What is the initial velocity in the y-axis? 0. Let me put a little x there just to emphasize that. What is the acceleration in the y-axis?
9.8.
9.8. Now, you need to get in this habit of choosing positives and negatives. Okay, it's going to get more and more and more important as we go along. Choose which way you want to be positive and which way you want to be negative. You want negative 9.8? Okay, let's call down negative and up positive. Fine with me. Down negative, up positive. That means I've got a negative 9.8 meters per second squared. What else do I know in the y-axis?
What y?
I know my y, or my displacement, right? 220 meters. I don't know the time, right? Nor do I know the final velocity. Now, step 4 says go to the axis with the variable that you want, try to solve for it. So the axis variable, my answer, is which one, x or y? X. So I want to solve in the x, and the only equation to choose in the x is the constant velocity equation, v equals x over t. X, S, tomato, tomato. Okay? I'm going to use X to make sure we don't get confused as to which axis. Right, so V equals X over T. Well, I've got V. I'm looking for X. I don't have T. I need T to be able to solve. Where can I get it from? The Y. So let's come over here to the Y-axis. Let's write ourselves an equation that allows us to solve for T. So given what we know, how can we solve for T? Give me an equation. In projectile motion, 99% of the time, that high, 99% of the time, these will be the two equations you use. V equals X over T for the X-axis. Y equals UT plus 1/2 AT squared for the Y-axis. I'm not saying every time. Maybe I should lower it to about 90%. Now, you will use other equations, but this is more than likely what you're going to use. Okay? So this sets up as 220 equals UT. What does that become? 0. My initial velocity is 0, so UT all becomes 0. I don't have to worry about it. 1/2 negative 9.8 T squared. All right, so solving for T. T is going to be the square root 2 times 220 divided by negative 9.8. And I know you're freaking out right now about that negative 9.8. We missed the negative somewhere else. Where did we miss our other negative? The 220, right? We were going down 220 meters, so that should be negative 220. That puts a negative here and a negative there to get all that to work out.
How negative can you add it to?
Well, we're not adding here. What do I have to do? Divide. Let me come back. I think I skipped steps. Right? Well, let's not do that. I apologize. Delete. Give me more space. All right. So now I'm going to have to divide both sides by 1/2 of 9.8, right? To get T squared by itself. So I have negative 220 divided by 1/2 times 9.8 equals T squared. Everybody see that?
Why is it negative 220? Why is it a negative 220?
Because we were going downwards. I said down was negative, and we're going 220 meters down.
Okay, I just leave both of them positive and then work out too.
Yeah. You could call, but be careful there. You're calling down positive. Right now, there's nothing going up, but eventually, we're not going to do it horizontal launch. We'll do it, with an angle, which means your initial velocity of the Y would have to be negative to all down positive. Right? Be careful. All right. I got to get T by itself. I got T squared. So I need to square root both sides. Right? So negative 220 over 1/2 times negative 9.8 square root is what T comes out to be. And if you would like I did previous, that 1/2 of the denominator could become a 2 in the numerator. Doesn't matter. Okay? That's 2 to the negative 1 in the denominator, right? Which means whenever you pull it up to the numerator, it just becomes 2. But never mind that for now. If that makes you nervous, just, plug through. And so time comes out to be what? 6.7 seconds. 6.7 seconds. Now, technically, it's plus or minus 6.7 seconds. Why can we forget the minus part?
Because time is only positive.
Yeah, time's only positive. How are you going to have negative time? Last time I checked, time travel wasn't invented. Right? At least not yet. Okay? Time travel isn't invented. So now I take this time, and I plug it back in to my constant velocity, to my x-axis stuff. Velocity in the x-axis was, let me come back up, see, 23. 23 equals 6.7 x divided by 6.7 now. Okay? So I do what? Multiply both sides by 6.7, so 23 times 6.7 equals x. X equals what? 450. 154.1. Now we check sig figs. I was given 2 sig figs, 2 sig figs. I only get 2, so this becomes 150. X equals 150 meters. I hit a brick road, or I hit a brick wall, excuse me, with the x-axis, solving for what I needed to. If you need to think about this as a maze, do. All right, just luckily for you, there's only 2 paths, right? You start down the path that seems most direct. It's going to get you the answer that you want. And if you find out you run into a brick wall, you don't have enough information, you go to the other path, you get the information that you need so that you can come back and get through. Okay? Questions about this problem? All right, next. I mean, these are pretty straightforward. Bullet shot horizontally at 290 meters per second, lands 164 meters away. How high above the ground is the guy holding the gun? So I've got some guy here, right? And guns are always bad for me. So guns for me always look like bazookas. So
Why is he?
there you go. I'm looking for y, right? I'm looking for what the height is here, y. The bullet comes out with an initial velocity of 290 meters per second, and it's going to go something like that, right? Before it hits. And it hits a distance of 164 meters away. So now we're going to do the exact same thing. Divide everything into components. Now, luckily for us, everything is already in components, right? The velocity is only in the x. I don't have to divide into components. The distances are purely in the x and the y. Okay? I'm mentally dividing into components by treating x and y separate. Time is the same for both of them. It doesn't have a component, right? Time is not a vector. Okay? Time just is. Time is a scalar. Acceleration is only in the y. So, I mean, here we go. The x. In the x, I've got a v equals 290. I've got an x equals 164. Let me stick correct units on this. T equals, I don't know anything about time. Y. Uy, where the initial velocity in the y is 0. The acceleration, if I call down negative and up positive, negative 9.8. Y, the displacement, is what I'm looking for. Right? And I don't know anything about time.
How is the, I don't get the initial y, and how is it there?
Look at this vector right here. Okay? If you had to give an angle to this vector, the 290 meters per second, what angle would you give it? 0 degrees, right? So punch it to your calculator. Everybody do this in fact. Let's go ahead. We have all decided that the angle that is being shot at is 0 degrees. So punch into your calculator, 290 sine 0. Well, because that's the initial velocity, right? So To get the component, right? To get the component, we take the vector, the y component, sine the angle. So 290 sine the angle comes out to be what? 0. Now take 290 cosine 0. 290. Okay? This is purely on the x-axis. Horizontal launch means purely on the x-axis. Okay? So, I don't have enough information in the y. I can already see that. Do you see that? What do I need? Time. I need time. Where can I get time from? The x. So let me come over here to the x. Correct. 290 equals 164 divided by t. T equals whatever 164 divided by 290 is. T equals what? 0.57 seconds approximately. I can drag that up and use it there. Time is the same in each axis. Okay? I can go ahead and tell you we're going to want our favorite equation here. Y equals ut plus 1/2 a t squared. And luckily for us, the initial velocity, once again, is 0 in the y because it's a horizontal launch. So that leaves me with y equals 1/2 negative 9.8 0.57 squared. So what does y turn out to be? Sorry? 1.6 meters? So somewhere around negative 1.6 meters, rounding sig figs, and you can come out with negative 1.56, negative 1.59, but whatever, it depends on how far you rounded your time off. Okay, that's what it depends upon. So negative 1.6 meters. Why negative?
Down is negative.
Because down is negative and the bullet went down. So if I asked you instead, how far did the bullet drop? If I said, like I did in this problem, from what height was the bullet shot, you would say, what? 1.6 meters up, right? 1.6 meters up is from what height it was shot. So then it would be positive 1.6, since we asked from what height. Double check. How high above the ground was the man holding the gun? So 1.6 meters above the ground. Yes. No, not at all. Yeah, if you want to call it down positive, that's fine. Just make sure that you call up negative, right? You just got to make sure they're opposites, up and down. Okay? Any questions? All right, let me give you a few problems to try, and then if we have time, we'll talk about it.